Today we're going to be learning about some calculations that have to do with acids and bases, like calculating from pH to pOH, or from pOH to the hydroxide ion concentration and back again, or from the pH to the hydrogen or hydronium ion concentration and back again, and from the hydronium ion concentration to the hydroxide ion concentration and back again. It's basically a big wheel, an acid-base calculation wheel. So we're going to start looking now at how to calculate pH, pOH, and the molar concentration of hydrogen or hydronium ions and the molar concentration of hydroxide ions from each other. In other words, you can go from any one of these to any of the others if you just know how to do the math. So this is kind of a big square. The corners show the different numeric values. Okay, the different measurements or concentrations or pHs or pOHs, those are numbers. Those are things for which we want to know values. And then as you get from each one corner to the next corner, and you can't go across the middle, you can only go from one corner to the next. In the middle there, it shows you how you calculate one from the other. So let's start in the upper left for a minute and look at the hydrogen ion concentration or hydronium ion concentration. Now, both of those will have the same numeric value. Hydrogen ion concentration is the way we judge the concentration of an acid or the working part of an acid in the Arrhenius acid-base theory, whereas the hydronium ion concentration is the way that we judge the working strength of an acid based on the Bronsted-Lowry way of thinking about things. And when you calculate them, because of the way we calculate them, you get the same value for both. To go from hydrogen or hydronium ion concentration, upper left, to hydroxide ion concentration, upper right, you use that Kw equation that's shown there in the middle. And the value of Kw is 1.00 times 10 to the negative 14 molar squared. Molar meaning molar concentration squared. All right, let's go back again to hydrogen ion concentration and hydronium ion concentration and find the pH. To find the pH, you're going to use the equation that it shows in the box where pH equals the negative log of either the hydrogen ion concentration or the hydronium ion molar concentration. To go from pH in the lower left corner back up to the upper left corner, you're going to take the pH value and put it as an exponent on 10 with a negative sign in front of the pH value. The point here is, or one point that you can draw from this is, and you should know anyway, is that a logarithm is an exponent. Now, unless we specify what the base is for the logarithm, it's always assumed to be base 10. So when we have an exponent, say an exponent 2 on a 10, that means the logarithm of that number, 10 squared, the logarithm is 2. So a logarithm is an exponent. So once you get the logarithm, the way that you find the original value is to put that logarithm in an exponential position on 10. All right, let's go back over to the upper right now and look at hydroxide ion concentration. To go from hydroxide ion concentration down to the bottom right-hand corner for pOH, you just take the negative log of hydroxide ion concentration, the same thing we did with the hydrogen ion concentration and pH. To go the other way, from pOH back to the hydroxide ion molar concentration, you're going to take the pOH value and put it as a negative exponent on the number 10 for the same reason. And then lastly, let's look at the bottom two, the bottom left and right. pH is related to pOH in this way. 14 is equal to pH plus pOH. So if the pH is 4, the pOH must be 10 because pH plus pOH, 4 plus 10, has to equal 14. So if you know these, it's easy to calculate any one of the others. All right, if we start with this problem, you have a solution with a pH of 3.26, and the first thing we're going to do is find the hydronium ion concentration. Hydronium ion concentration is determined from pH by putting the pH as a negative exponent on a base of 10. So pH is a negative logarithm. Logarithms are exponents. We undo logarithms by putting them on the base as an exponent. So here's pH, 3.26. Hydronium ion, that's what this symbol H3O plus is. The brackets mean molar concentration of what's inside. So the molar concentration of this is 10 to that negative exponent of 3.26. And this is the answer we get. This long number, that's the molar concentration of hydronium ion, and rounded off we get this. So what is the hydroxide ion concentration? Well, we use this equation. Kw equals hydronium ion molar concentration times hydroxide molar concentration. The value of Kw is 1.00 times 10 to the negative 14 molar squared. On a lot of test references, you'll find a lot of these. In this case, it says Kw equals hydroxide ion molar concentration times hydrogen ion molar concentration. Well, hydrogen ion molar concentration is the same value as the hydronium ion molar concentration. What's here is how we represent acid concentration for the Arrhenius acid base theory. H3O plus, here, hydronium, is how we represent acid concentration in the Bronsted-Lowry acid base theory. So we're going to plug in this number for this value, plug in what we know about Kw. It's 1.00 times 10 to the negative 14 molar squared. It's that number there, only it's a little more expanded than what I just told you. Plug all that in, divide both sides of the equation by this number so we can cancel that out and get hydroxide ion concentration by itself. Divide here, and we'll get this number here. You need to be careful about putting this in your calculator. A lot of students make the mistake of not keeping all of the orders of operation correct. So I would suggest you put this entire top number here in parentheses. Then divide by this entire bottom number in parentheses. If you don't have a better quality graphing calculator or just scientific calculator, you can get an answer by taking this number divided by this number, then taking this exponent and subtracting this exponent and putting it all back together again. A little more complex. A better quality scientific calculator makes the math a little bit easier for you to do. All right, so what's the pOH? Well, that's the negative logarithm of this. pOH is the negative logarithm of the hydroxide ion molar concentration. We get this number rounded off to 3 significant digits. So now let's try practicing this problem. If a solution has an hydroxide ion concentration of 2.37 times 10 to the negative 8 molar, what are hydronium ion concentration, pH, and pOH? So now you can compare your answers to what I calculated here. Your answers may be slightly off from this and still be correct, because what we're really doing here is propagating an error because we're rounding off between one problem and the next. And that rounding off between one problem and the next propagates the error. If you wanted to get the best possible answer, is you would do all these calculations without any rounding off, and before you report these answers, round off at the very end. So lastly, here's a homework problem for you to try. If a solution is formed by dissolving 2 grams, 2.00 grams of sodium hydroxide in 250.0 liters of solution, what are the pH, pOH, hydronium ion molar concentration, and hydroxide ion molar concentration? Now you're going to have to calculate the concentration of the solution on your own. So using what you've been taught in previous units, you need to take that 2 grams of sodium hydroxide and convert that to moles using molar mass. Then you take the moles and put it over the liters of solution to find the molar concentration of sodium hydroxide. You need to know how many hydroxide ions there are in sodium hydroxide, and the molar concentration of sodium hydroxide gets multiplied by the number of hydroxide ions in this formula. I want you to get out this chart. Get out this chart that I gave you. This is the first and only time where I've given you a reference that you will be allowed to bring to the test. Okay? The test references, the regular test references, you have to use mine. but you can bring this sheet with you. Okay? It's just printed in color. It's a lot of expense to try and reprint it, so just make sure you don't have anything written on this sheet. Okay? If I see something written on here, then that's assumed to be cheating. Don't put me in that situation. Don't put yourself in that situation. All right, in the most recent lab, we produced a pH curve for an acid. We found the entire curve, and then I expect you to find that point of inflection on that pH curve, which represents the point of equilibrium, or what's that word I'm looking for here? Equivalence point. The equivalence point to find, and when once you find the equivalence point, you can find the volume of the base used to titrate your acid. Can you guys in the lab be a little more quiet, please? Thanks. In reality, when titration is done, and titration is one of the most common lab techniques there is. In reality, the experimenter almost always knows what the point of equilibration is going to be, what the pH of the equivalence point is before they even go into the lab. And so what they would do is just simply titrate to the point of equilibrium or point of equivalence and stop. All right? You can do that with a pH meter, but sometimes pH meters don't give you exactly what you want because you're equilibrating or you're titrating other things besides acids and bases. And so you might use something like this. These are color changes for acid-base indicators. You see, there's a lot of them. This is not an exhaustive list. There are other acid-base indicators, colored acid-base indicators. If you've ever had purple cabbage, let's say you go to the salad bar at some restaurant, and one of the things you see in there are some green leafy things, or they're leafy things, but they're sort of white and purple. That's purple cabbage. If you take purple cabbage, go to the grocery store and buy purple cabbage, boil it, you'll get purple water. That purple water is an acid-base indicator. If you change the pH by adding baking soda and or vinegar and changing it back and forth, it'll go from clear to purple at a certain pH. I don't know what it is off the top of the head, but it will do that. So that's a kind of a natural or easy to find or use acid-base indicator. But here's how they work. Let's say I've got an equivalence point for a certain acid I'm titrating of 3.5. I've got an equivalence point of 3.5. So if I'm titrating an acid, I want to be going from a low pH to a higher pH. We're going to start with maybe a pH of 0, 1, 2, somewhere down in here, and I'm going to add base to it, and the pH is going to go up, just as it did when you did your pH curve in your lab. So if I know the equivalence point is at 3.5, then I want to go up to 3.5 and find an indicator that's just going to barely begin to change color at 3.5 and choose the indicator that best gives me the results I'm looking for. So looking at this, I can see I might choose bromphenol blue, or I might choose methyl orange, because methyl orange is just barely beginning to turn sort of a yellower color at that point. And bromphenol blue, while it's changing color there, it's kind of gone past where it started to change color down here. Okay, so this might be a better choice. The only problem is it's hard to tell when you're going from orange to yellow. So you have to kind of make your best choice as to which one's the best one to use. But if I were to ask that question, what indicator would you use? You would choose one of those two, and I'll give you credit for either one at this point in time. Now let's say you have a base, and you're titrating that base. The base is the analyte. You don't know its concentration. You're titrating it with an acid. Then instead of the pH going up, the pH is going to go down. So if you have an equivalence point of about, let's say 8, all right, and I'm titrating a base, then I want to go from the other direction. So I'm going to sweep, instead of going sweeping up, I'm going to sweep down and find a color change that begins right at 8. Okay? What would you choose?
The blue one.
Okay? Let's see. Okay, that one right there at 8. Okay, yeah, you might be able to use that one. I probably would choose phenol red because that's That one actually gives you a better indication. Going from blue to green is really hard to see, but you wouldn't know that. Okay, I would give you credit for either one of those. All right, because at this point in time, you don't have enough experience to choose the best one down to that degree. Just so long as you choose one that gives you the beginning of a color change where you need it. You understand what's going on? And that's how you use it. So most of the time in the lab, if you were actually going to equilibrate or reach the point of equilibration to find that the concentration of some acid or base, you might use a colored indicator like this to get that. All right, and that's what it's used for. And nowadays they have instrumentation, especially those that go from clear to some color. The instruments will actually register that. I mean, or you can have it register red wavelengths or something. So you can actually have instrumentation that reads the color change. And that's a good way to do it. So the instruments do a lot of things we used to have to do by hand or just by eyesight. But now we can do it with instruments. But you still need to know how it works and why it works, so that if the instruments aren't working, you kind of got to be able to figure out why. Okay? Just like I have to try to keep the equipment working in here sometimes when they don't seem to work that way they should. All right? You got that? So on the test, if you're asked a question about color indicators like this, this is the tool you use. Any questions? Okay then. Let's talk a little bit about an acid-base theory we haven't talked about so far. So far we've talked about the Arrhenius acid-base theory. In the Arrhenius acid-base theory we said that acids are any chemical species that donate hydrogen ions or protons to the solution, and bases are any chemical species that donate hydroxide ions to the solution. We said Bronsted-Lowry acids and bases. Bronsted-Lowry acids are any chemical species that donate hydrogen ions or protons to another chemical species, and bases in the Bronsted-Lowry theory are those chemical species that accept a proton from another chemical species. But Lewis came up with a different idea. Y'all remember that name, Lewis? Lewis dot formula. And guess what? This has everything to do with those Lewis dots. Imagine that. Okay? Now here's the thing to remember. Arrhenius acids and Arrhenius bases are also Bronsted-Lowry acids and bases. And Bronsted-Lowry acids and bases are also Lewis acids and bases. But when you go the other direction, it's not always true. Not all Lewis acids would be Bronsted-Lowry acids. And not all Bronsted-Lowry bases will be Arrhenius acids, or bases rather. Okay? So you've got to know that as we sort of go through these theories, Arrhenius is the one that's the least inclusive, the simplest, but the one that doesn't cover as much. Bronsted-Lowry is more inclusive, covers more stuff, but not as inclusive as Lewis. Okay? So here's how Lewis defined acids and bases. In the Lewis theory, acids are any chemical species that accepts a pair of electrons in a covalent bond. So acids are any chemical species that accepts a pair of electrons in a covalent bond. Now, remember that in any sample of water, there's no such thing as pure water, because a very small number of any sample of water has a very small number of hydrogen ions and hydroxide ions in it, because the water molecules occasionally dissociate. Okay, so water will break up a very, very small number of them, 10 to the -7 molar concentration will break up, and so you get a very small number of hydrogen ions and a very small number of hydroxide ions. Okay? So if I take and put into this sample of water, this larger sample of water, some ammonia, there's going to be some hydrogen ions in that water because a very small number of them are breaking up. And this is actually it goes back and forth. So some of these are going back that way, some of these are going this way. This is a Le Chatelier system. And so if I put into this water where these hydrogen ions exist some ammonia, what is that hydrogen ion going to want to do? Where? Bond to the top where the lone pairs are located. So this chemical species here is going to accept this pair of electrons in a covalent bond. And because this chemical species here came from this one, this is a Lewis acid, and you would also say this is a Lewis acid. Okay? They're kind of one and the same. Okay? Alright, that's a Lewis acid. By the definition we gave for Lewis bases, it's a chemical species that brings a pair of electrons to a covalent bond. Bring it up here. Lewis base is any chemical species that brings a pair of electrons to a covalent bond. Well, that means this ammonia must be a Lewis base because it's bringing that pair of electrons to this covalent bond. So what we're actually forming then is ammonium. Because I brought a positive charge to this neutrally charged particle, this particle has a positive charge. Okay, so that's ammonium there. So I can also write it where I start with the water and put it with the ammonia. This hydrogen ion then goes over here and joins up. This hydrogen ion shares that pair of electrons in a covalent bond. And so we're going to get ammonium. And because the hydrogen ion came off, what's left then of this species here is the hydroxide ion. Okay? So because the hydrogen ion came off of this is the Lewis acid. And this is the Lewis base. Okay, these also happen to be Bronsted-Lowry acids and bases. This is a Bronsted-Lowry base because it accepts a proton from this. Okay, this is a Bronsted-Lowry acid because it gave up a proton to this and it'd be joined up with this one to another species. Okay, in the Bronsted-Lowry system, this is the conjugate acid of the base. This is the conjugate base of the acid, of the Lewis acid, or the Bronsted-Lowry acid. Okay? Now you don't have to know how to do any calculations with these. You just got to know the theory and be able to illustrate it. Okay? You got to know what the Lewis theory is. Lewis acids are any chemical species that accept a pair of electrons in a covalent bond, and a Lewis base is any chemical species that bring a pair of electrons to a covalent bond. And in fact, in the textbooks and probably on the internet, they would refer to the bases as anything that donates a pair of electrons. Well, the problem with that definition is a lot of students hear that and they think, well, that must mean that something has to give up a pair of electrons. That's not what happens. Okay, that's why I prefer to use the term that it brings a pair of electrons to a covalent bond. There are 4 strong bases, and unlike the acids, I don't have an easy way for you to sort of figure out when they're strong acids, okay, or strong bases. Remember, with acids, we said if the acid is binary and the anion is one of the halogens other than fluorine, it's strong. And we said if the acid is an oxyacid, that means it contains oxygen, and you have 2 or more oxygens than the number of hydrogens, that's also strong. That was kind of an easy sort of way of being able to recognize strong acids. We don't have that for bases, but luckily there are only 4 strong bases you have to know about. Okay? I'm not sure who came up with or why these are the 4 strong bases identified in the state standards, but that's what I'm giving you. Okay?